Now, this time we're more interested in looking at functions. Problem is, in a normal diagram there, I can draw a function quite easily because y and x are both real numbers, and I can use a vertical axis to represent the y coordinates. I can use a horizontal axis to represent the x number. And I sub the x number into a formula, and I get a y number, and we can draw a nice picture. Problem is, I now can't do that because we're using both the y-axis and the x-axis to represent one number. So the whole number plane is representing one number. And now if I substitute it in, I basically now need a four-dimensional number plane, which obviously we can't draw. Okay. So what it is we look at is we say, okay, we have one number plane for the input, or one Argand diagram for the input, and we'll have one Argand diagram for the output. So we'll put in all the complex numbers that satisfy the requirements into our function, and the output we'll put on a different Argand diagram.
Why is it 4 dimensions?
Well, because, see how that's two-dimensional? Because your real equation has y equals something x, so you've got to deal with two numbers. So you need 2 dimensions to make a graph of the relationship between y and x. But we now need 4 dimensions because we need 2 of them to represent one number, the real part and the imaginary part of the number we're using. And then we need another 2 to represent the answer, the real part and the imaginary part of the answer. Well, I can't physically do that on one diagram. So it's not a big deal. We're just thinking of it. We don't always draw 2 diagrams. But the way we think about it is we're saying, hey, we're going to get all the numbers from this diagram, substitute it into the function, and then we'll draw the answer on the other diagram. No different really to what we were doing with the parabola and the hyperbola and so on. We're saying we're getting all the numbers on the x-axis, we're substituting into a function, and we're getting answers. We're getting y values, and we plot the answers. It's the same idea. So don't get too hung up about this 4 dimensions. It's like, oh my gosh, 4 dimensions. It's not that big a deal. So we're going to have omega is some function of z. Right? We're going to have a function. We're going to substitute a complex number in z, and then we'll get an answer out. It's going to be omega. Okay? So we're going to, and then they'll ask us to say, well, what is the locus of omega or z, the original one or the answer? And then they'll usually give us some condition for the original one or the answer. So it might be that on the original graph, we know the modulus of every number is 2. So we're going to get all the points that are on this circle. Put it into the function. What sort of picture will come out on the other one? Will it still be a circle? Will it be something else? The idea is make the condition the subject. That's probably the easiest way of dealing with these problems. Couple of obvious ones, if we see them straight away, ideas to think of. If they're telling me omega is purely real, then the condition I've got on that, I could think of it as the imaginary part of omega is 0. That might be the condition I'm playing with. I'm going to get all the numbers on the x-axis, basically, and sub them in. Or it might be I'm going to use the idea that the argument is either 0 or pi, because that would be the other feature of a purely real number. And similarly, but in the other direction, if it was purely imaginary, I know, okay, well, the real part is always going to be 0, or the arguments would be plus or minus pi on 2. This one's interesting. If you see the argument of, this is the condition, and I'll go argument of, and then on the top of the fraction you've got some linear function. So it might be a z plus 2 or whatever. And on the bottom you also have a linear function, z minus 3i. Equals some angle, the locus will turn out to be an arc of a circle. It'll always turn out to be an arc of a circle. Now, it'll be a minor arc if theta is greater than pi on 2. It'll be a major arc if theta is pi on 2. And we get a semicircle, theta is pi on 2. It basically comes from angle in a semicircle idea. We'll have a look at the example later and we'll see what I'm talking about there. So, okay, here it is. Find the locus of w. In other words, what will this picture look like? There's our function. W is equal to z plus 2 on 2. So no different to what we've been doing in coordinate geometry, except we'd have y and x's. we'd say, oh, draw y equals x plus 2 on 2. Well, I can't draw it when I'm talking about complex numbers. I can do it if I was doing real numbers. So that's why I'm saying we have two diagrams. I only need to draw one of them because it says find the locus of w. We know already all the numbers for z that we're going to sub in. We're going to sub in all the numbers that lie on that circle. The modulus of z is equal to 4. So that is the condition I know. So I'm going to try and make z the subject of this function that we're dealing with. W equals z plus 2 on 2. Oh, sorry, it was a misprint. Should have been z on the bottom, not 2. W equals z plus 2 on z. Those curly 2s are much better. So I'm going to rearrange this and make z the subject. So I've got zw is equal to z plus 2. So I'll factorise, and now I can make z the subject. And now I can work out what the w picture is going to look like. Because I know the modulus of z is equal to 4. And if z equals 2 on w minus 1, therefore the modulus of that must equal 4. And I now have got something I can work with and go, what does this picture look like? So we know now that the modulus of 2 on w minus 1 is equal to 4. What does this picture look like? Not immediately obvious. Play around with it a little bit and it becomes obvious. I know the absolute value of 2 is 2. If I turn it upside down and move the 2 to the other side, we get modulus of w minus 1 is a half. Ah, what does my new picture look like? What's another circle? Centre would be at 1 and its radius would be a half. So if I was to, over here on my left-hand side, this is all my z's, they all sit on this circle, substitute it into this function, I'd get a new circle. Its centre would be at 1 and its radius would be a half. The only thing we have to be careful with here, and in this case it looks all right, because I would not be able to substitute in the point 0, 0. But in this case that's okay. 0, 0 is not on my circle, so I don't have a problem with my answer then. So you just need to look out for little things like that. Is there a point that I can't substitute in so I wouldn't get an answer? Okay, this time, there's our function. W is equal to z plus 1 on z minus 1. But this time, they're telling us the answer. If I was to draw the W picture, I'd get something which is purely real. So it's going to be the real axis. So all the answers will be the real axis. What did I substitute in? It's already made W the subject for me, so that saves me a bit of time. So z plus 1 on z minus 1 is purely real. So if I go back to algebra, I'm not sure. So I'll go back to the coordinate geometry idea. If I want to get the real part of this, I need to realise the denominator. So I multiply by its conjugate. Bottom I get x minus 1 squared plus y squared. The top I get that. I don't need to expand the whole top because all I'm really interested about is the imaginary part, because I know the imaginary part of this will equal 0. So if I pull out the imaginary part, and in fact I don't need the bottom of the fraction either, because I've got a fraction equaling 0, it's going to be the top of the fraction that equals 0. So I'm now left with this. Okay, let's play around with it. See what we get. I get y equals 0.
So you can't have 1, 0, can you?
Ah, very good. So now we go back to here and we say, well, all right, I could not substitute in the number 1. It satisfies y equals 0, but I wouldn't be able to substitute into the function. So yes, it would exclude 1, 0. Another way to think about it is instead of saying the imaginary part is 0, I could think of it using the argument. And this sometimes can be a lot quicker. If w is purely real, then I know the argument of w is 0 or pi. So I'm saying the argument of z plus 1 on z minus 1 is 0 pi. So the difference between the arguments is 0 or pi. Let's draw a picture. There's 1, there's minus 1. I have to place Z such that the difference in the arguments would be 0 or pi. Where do I place Z? So they've either got the same argument, the difference is 0, or they differ by 180 degrees. It's got to be a straight, that horizontal line that contains both points. That's the only place I could put them. So there would be points over there that would satisfy here, because if I put Z over here, the argument going from 1 would be 0, the argument going from -1 would also be 0. Difference is 0. I could put it over here, similar idea, the difference would be 0, both going in the middle, their difference would be pi, because one would be going to the left, one would be going to the right, their difference would be there. But you'll notice I've circled -1 and 1. Yet over here, when I did it with algebra, I only got the exclusion of 1. Which one is correct? So there we go. I've got excluding both points. And it all comes down to what was the original question. That's the original question. Does it work? Have a look. Over here, I'm excluding 2 points, plus or minus 1. Does it work? Well, we know this one doesn't work. We know 1 doesn't work. We already checked that. Let's have a look at -1. If I put -1 in that, I get 0 on the top. I'll get -2 on the bottom. So I get the answer 0. Is 0 purely real? Yeah, I mean, it is that funny number, but we consider it purely real. So in this case, I don't exclude both of those points. Right? I answer the original question. If the original question was that the argument was 0 or pi, then I would exclude both because it wouldn't satisfy that one. But I've used this question to answer the original question. So it's created another solution. It's like when we looked at equations, and if we multiply both sides by x, we turned it into a quadratic and we created extra solutions. It's sort of like that idea. I've created some extra problems here that actually weren't problems. All right, here comes the fun one. There it is. The argument of, on the top of the fraction, I've got a linear function. It's just z. Bottom is z minus 4, and it equals pi and 6. This is an arc of a circle. Right? Let me show you why. What we're saying again is I'm going to place it such that the angle between, when I join it up to 0 and when I join it up to 4, the angle will be pi and 6. The difference in the arguments is pi and 6. So let's have a look at the picture. There's 0, and I've just drawn a random ray. Z could be somewhere. There's 4. I've drawn a random ray. Turns out it means that the angle between the two will be pi on 6. You can play around with the geometry to prove that, because we're basically saying the difference in the arguments, exterior angle is the same as the sum of these two. So the difference would be that one up there. That's why we get an arc of a circle. I'm getting 2 points, joining it up to a third point, and the answer's always going to be pi on 6. Angles in the same segment are equal. And so that's why I end up with an arc of a circle. I get the segment that involves that. The tricky part is finding the equation. Okay, I'm below the axis because the argument of z has to be bigger than z minus 4, because it ends up with a positive number. If I was above the axis, if I drew the answer above the axis, then the argument of z would be smaller. But because I'm below, I'm dealing with negative numbers, that sorts it out. So in reality, the way I would check it, I drew it underneath here straight away because I knew what the answer was. But in reality, if I got a question, I'd probably look at it on top first. I'd do something like this. I'd say, well, my 2 points are 0 and 4. If z's on top, and then I'd have a look at it. Argument of z, I'll call that alpha, z minus 4. Alpha minus beta is positive. Is alpha minus beta positive? No, it's not. Beta clearly is a bigger angle. Therefore, it must be underneath, not above. So that's how I'll check whether I'm above or below. Okay. Let's now, well, what else do I know? I know when I've got a chord, perpendicular from the center will bisect the chord. So I know that it must be lying on, so let's just join in. Whoop, keep drawing. There we go. The center must be down here somewhere because I'm talking about a major arc. Perpendicular from center. Well, my chord's horizontal. Therefore, the perpendicular from the center must be vertical. So I know the x coordinate will be the midpoint of 0 and 4. So it's 2. Now I just need to work out the y value. Okay. Well, the radius would be the length of that hypotenuse there. I know that angle there is going to be 30 degrees because the angle at the center will be twice the angle at the circumference. But then I'm only talking about half of that. So I've, in fact, got the same angle. So what I've now got is y over 2 is the tan of 60. The y value, well, it's not 2 root 3 because it's below. It'll actually be negative 2 root 3. So I now know the centre is 2 minus 2 root 3. The radius, bit of Pythag. We know the radius is 4. We have our answer. The locus is the major arc of that particular circle, formed by the chord joining 0, 0 and 4, 0, not including those 2 points because the starting point of the ray is not included. Isn't that fun? Isn't that fun? Well, you've got to describe them. So it says find the locus. So, yeah, you sort of need to describe all that sort of. Yeah, it's good, isn't it? All righty. I'm sure we'll have